All right, AP Chem. Today we are going to do some KSP practice problems together. The first problem is going to state the value of KSP for AgCl is 1.8 times 10 to the minus 10. So KSP in this case is 1.8 times 10 to the minus 10. What would be the molar concentrations of Ag plus and Cl minus when solid AgCl is placed in pure water? So let's write down what that means. The chemistry sentence that matches that English sentence is as follows. Solid silver chloride, and remember this is a slightly soluble equilibrium dissolving of a salt, and it's going to dissolve into Ag plus 1 ions and Cl minus 1 ions. So this is the KSP law, essentially. KSP law states that when you put slightly soluble salts in solution, they will dissolve, not a lot, but they will dissolve into some ions. So the KSP expression is just like the K expression. You're going to write products over reactants, but in the case of KSP, the reactant's always going to be a solid, so it's not going to be included. So my KSP is going to equal the concentration of silver ions times the concentration of chloride ions. And remember, I'm going to do an ice chart for you. You don't have to do an ice chart every single time. When you get used to what the pattern is, you won't have to do them at all because the solid is not included. And before we dissolve, the initial situation is going to be that we don't have any ions of these in the beginning. But when the change happens, we're going to get some ions. For every one silver ion, we get one chloride ion. Therefore, the concentration at equilibrium for each of those is going to be X. So it's going to be X times X or X squared. Just remember, when you have two ions, the expression is always going to end up simplifying to KSP equals X squared. So I'll simply take the square root of each side, and that's going to give me a value of X as 1.34 times 10 to the minus 5. So the concentration of silver is going to equal the concentration of chloride, which is going to equal 1.3 to 2 sig figs times 10 to the minus 5th molar. So there's an example of a KSP problem with two ions. Number 2 states that what are the molar concentrations of ions in solution when solid PbI2 is added to pure water? The KSP for PbI2 is 7.9 times 10 to the minus 9. Now, remember, we did talk a little bit about equilibrium. So is the KSP always going to be exactly the same every time you use the same salt? What is going to change the value of KSP? Temperature. And that kind of makes sense to us what we already know about dissolving salts, that salts will dissolve differently in different temperatures, and the more you raise the temperature, the more the solubility will increase. So here's the KSP law. We'll do an ice chart again. And one more time, I'll mention you're not going to always have to do the ice chart, just until you get comfortable with the patterns that we're going to see. So KSP will be the concentration of lead times the concentration of iodide ions squared. And when we plug in X and 2X, we'll notice that 2X is squared. So that means the 2 squared, and so is the X. So it becomes X times 4X squared, or 4X to the third. So we'll divide by 4 and take the cubed root of that. So the value for X in this case, after we divide by 4 and take the cubed root, is 1.255 times 10 to the minus 3. So that means my concentration of lead is going to be equal to X, or 1.3 times 10 to the minus 3 molar. And my concentration of iodide is going to be 2X, or 2.5 times 10 to the minus third when you round to 2 sig figs. So here's an example of an ice chart for when we have 3 ions, and 3 ions will always have the pattern Ksp equals 4x to cubed. Number 3, what is the solubility of CaCO3 if the Ksp is 8.7 times 10 to the minus 9? Now, when they say solubility, this is a little bit different. They're not asking us for the concentrations of the ions. They're asking us how much will dissolve. So really, they're asking you the value for that X. I want to point out, when you're looking up problems, like if you go on the internet and try to find some other problems, some people are going to list, instead of X in these problems, as S. They're going to list it as S. So don't let that confuse you. I'll do an ice chart for you with X if it's helpful. So for every 1 piece of calcium carbonate that dissolves, we will get 1 piece of calcium and 1 piece of carbonate. So this is 2 ions, so I'm going to go straight to Ksp is equal to X squared. And where they're asking you the solubility, they're asking you how many pieces of calcium carbonate will dissolve. That's always going to be your value of X or S. That's because you're always going to have 1 piece dissolve, and it'll fall apart into however many ions, but that value of X is what we're going to be concerned with. So we're going to take the square root, and my value of X is going to be 8.7 times 10 to the minus 9. Oh no, that's the value of X squared. So the value of X is going to be 9.3 times 10 to the minus 5. That's how many moles of this will dissolve in a liter of solution. So that's your answer for the solubility, which, like I said, is sometimes listed as S. Next one says, what is the Ksp for calcium oxalate if the solubility of the salt is 4.8? times 10 to the minus fifth moles per liter. So that's your value in N. Ksp law is calcium. Now pay attention to this, because remember I told you you're going to have cations and you're going to have anions. And the only positive cation is going to be ammonium, and ammonium salts are all soluble. So you're always going to be looking at this going, I'm going to pull that first ion off, and the rest of it is going to be what's called a polyatomic anion, and this one is called oxalate. So if you haven't seen this one before, just know that as soon as I pull off the cation, the rest that is left over is going to be my polyatomic anion. So when you do this, let's do the ice chart so you can see the pattern. 0, 0 plus X plus X. And they gave you the value for X. So Ksp, in this case, is going to be the concentration of calcium times the concentration of oxalate, which is going to be X times X, or X squared, or 4.8 times 10 to the minus fifth squared. To two significant figures, that is 2.3 times 10 to the minus 9. That's the Ksp for calcium oxalate. Notice that in different problems, they're going to ask us for different things. When they ask you for Ksp, they'll probably give you X. When they ask you for X, they're asking you for solubility. They're going to give you Ksp. All right, number 5 is giving us the concentration of silver ions. So let's see what this means. We are calculating the Ksp, so we do not know the Ksp. We do know that the dissolution of silver oxalate is going to give me 2 pieces of silver, or 2 silver cations, for every 1 oxalate. So let's do the ice chart. No solids included. Zeros for these guys. This is going to be plus 2x, and this is going to be plus x. They also told us the concentration of silver in this solution is 2.2 times 10 to the minus 4. This is not the value of X. This is the concentration of an ion. So you got to figure out how it's related. So this is actually the value of 2X. So the value of X is going to be half of that. So when I'm trying to find Ksp, it's going to be the concentration of silver ions squared times the concentration of oxalate ions, which is half of the silver ions, or X. And multiply that through, and I get 5.32 times 10 to the minus 12. Does everybody understand the different things that they're giving us and the different types of problems? It's really the only tricky part of this is to figure out, what are they giving me and what are they asking me to find? Last problem in our example problems is for lead 2 bromide. And this time it's asking us to find the Ksp again. Did not give us the Ksp. This is how PbBr2 dissolves. 1 piece of lead and 2 pieces of bromide. So we're starting with 0, 0. This is plus x, and this is plus 2x. The concentration of lead in here is 2.14 times 10 to the minus 2. Now, the concentration of bromide is going to be 2x, so it'll be 4.28 times 10 to the minus 2. So now when I plug in Ksp, it's going to be the concentration of lead times the concentration of bromide squared. 2.14 times 10 to the minus 2, and then 4.28 times 10 to the minus 2 squared. So when we plug this into our calculator, let's see what it gives us. .920 times 10 to the minus 5. And we'll round to 2 significant figures again. 3 this time. So 3.92 times 10 to the minus 5 is my value for Ksp. Any questions?